The depletion region width, this equation, it is given from the JFET. We have derived this equation in PN junction diode. I'm going to use the same thing here. So the depletion layer width is given by H of x equal to epsilon into V of x plus VBI minus VGS by QND, the whole power of. V of x, it is the potential in the channel because of drain source voltage. VBI is the built-in potential of the depletion region. Epsilon, is the permittivity of the substrate. So now when you are going to solve this for V of x in equation 3.16 and differentiating V of x with respect to x. So I'm going to differentiate V of x with respect to x. If I do that, I'll get dV of x equal to Q ND H of x d H of x by epsilon. Okay, I'm going to get this equation. Okay, now I'm going to substitute equation 3.17 in 3.15 where I have dV of x, and I'm going to simplify. I want to explain the expression for drain current. So I'm substituting this equation 3.17 in the previous equation 3.15 where I have dV of x. So I can write I1 into dx equal to mu n into q nd the whole square w by epsilon into have all the terms as a function of x inside the bracket. A h of x into d h of x minus h of x the whole square into d h of x. Okay. And now if I want to find the drain current, I have to integrate on both sides. I have to integrate on both sides with respect to H1 to H2. So ID1 will be equal to mu n into Q nd the whole square into W by epsilon L into integral H1 to H2 AH DH minus H1 to H2 H square DH. Okay. I am just replacing all the function of x by normal thing. H of x will become h and d h of x will become dh, just for simplification. Okay, and you know that for a JFET, and the integration answer. So integration of ah dh is a, take it outside, you get h square by 2, apply the upper limit and lower limit, minus integration of h square is h cube by 3, apply the upper limit and lower limit. And we know the value for h1 and h2. H2 is the H2, the depletion layer with the drain terminal is given by this one, and the source terminal is given by this one. So at the source terminal, this VDS will not be there. So VDS will be 0. At the drain terminal, you will have the effect of VDS because I'm applying an voltage VDS. So this where is this equation coming from H1 and H2? From the barrier potential. See this equation H of x. From this H of x only, I'm writing the value for H1 and H2. So if I take H2, it is at the drain. So I'll be including VDS. If I take H1 is at the source. So I'll be neglecting VDS. See the diagram? H1 is at the source and H2 is at the drain. Source is grounded. And you see at drain, I'm applying an voltage VDS. That's why I'm taking VDS at the drain terminal, and I'm putting VDS equal to 0 at the source terminal. Okay. So now, and the pinch off voltage, this is the pinch off voltage equation, what we know. So now substitute everything. So H1 ID1 equal to mu n into Q nd square W AQ by 2 epsilon L into substitute everything. So in this equation, you have H2 square minus H1 square minus 1 by 3 into H2 cube minus H1 cube. So substitute everything. You have power 3 by 2 and 3 by 2. So the pinch off current is given by this. I'm going to take this term as the constant term, right? And the constant term, you take this 1 by 3 also outside. So if you take 1 by 3 outside, it becomes 6 epsilon L outside. So including that 6, I'm going to take that term as IP1. When I take this 1 by 3 outside, first term 1 by 3, so you have to multiply by 3. So see the simplified expression here, ID1 equal to IP1 into 3 VDS by VP naught minus 2 into this expression plus 2 into this expression. Okay, so above drain current expression is valid in the non-saturation region. Aதாவது non-saturation not till your pinch off voltage. So the current will slowly increase till your pinch off voltage. So where the pinch off current will be maximum if the zero bias depletion region is ignored or VGS equal to zero. The maximum drain current you will get when you put VGS equal to zero. Okay, so 3 point equation 3.25, what you have seen, this is the ideal equation for drain current for a MOSFET, and what you have seen and what we have been using throughout the uh, thing in formulas, this expression ID equal to IDSS into 1 minus VGS by VP the whole square is going to be the approximate version of the actual drain current. See the actual drain current, how many terms are there? IP1 into 3 into VDS by VP naught minus 2 into, it depends on all the voltage and the corresponding pinch off voltages. Okay, you cannot neglect all these things. And this equation is valid only in the non-saturation region, அதாவது when the current is increasing till pinch off. So till pinch off only the previous current is valid. So if you want to, if you are considering a two-sided symmetrical JFET, then the drain current will be 2 times the drain current. So I can write ID1 equal to G01 into VDS minus 2 by 3. I am just simplifying other things further. So I'm just having common terms. I'm taking out the common terms and simplifying. Here also I'm taking this 3P naught outside. So if I take this 3 by Vp naught outside, I'm going to consider that as G naught 1. So G naught 1 is equal to 3I1 by Vp naught into, only first term you will have only VDS. Second term, I have taken this Vp naught outside. So for that you will have this term root of 1 by Vp naught. ஏன்னா power வந்து 3 by 2 இருக்கு, கரெக்டா? So these mathematical steps, I think it is very simple. If you can do it, you can derive it once. You do it by yourself when you see the textbook, and each step, it is in the textbook, every step is given. Only thing you have to cross check whether the previous step is leading to the next step or the next step is leading to the next step. So you have to cross check that better. So if you do that, this will be the final simplified expression for ID1, the drain current in terms of the all the voltages for a JFET. And the symmetrical JFET, when you consider two N channels, the total drain current will be the current flowing through this channel plus current flowing through this channel. So ID1 plus ID1 will become 2ID1. That is what they have mentioned. When you consider a two-sided symmetrical JFET, two-sided means when you consider two separate N channels, then the current will be, two drain currents will be flowing ID1, ID1. So when you add both the drain currents, you get 2 ID1. So that's why we have used here the total drain current ID2 will be 2 into ID1 when you consider a two-sided symmetrical JFET. Okay. Channel conductance, other things, it is differentiate ID by Vs. So GD is going to be dou ID by dou VDS. Put VDS equal to 0. So you get very simple equation G01 into 1 minus VBI minus VGS by VP naught the whole power half. So this is going to be the channel conductance. So from the above equation, the conductance G01 is the conductance when VBI and VGS are 0. Put VBI equal to 0 and put VGS equal to 0. If you put both to be 0, then I can write GD equal to G01. That is the maximum value of channel conductance. This maximum value of channel conductance will exist when there is no depletion region in the channel. So when the depletion region start expanding, then the channel conductance will be reducing because of the gate voltage, whatever you are going to give. So in general, the ideal current characteristics of N-channel JFET is shown, where you can see at when the drain gets pinched off, you can say VDS equal to VDS sat. At pinch off, the device is said to be in saturation. Saturation, constant current will be flowing through your device. When you keep on increasing the voltage beyond VDS, then what happened? The device slowly enters into